In this summary video, we will take a look at what we call measures of dispersion or measures of variation. In the last video, we looked at what we call measures of central tendency. That is, we looked at where most of the values in a data set actually falls, whether or not it falls in the upper 25% or 75th percentile, in the bottom 25%, or we wanted to find out whether or not it was somewhere around the center. So we looked at values or measures such as the mean, the median. The mode gave us information on the frequency of some of the numbers, and the number that is most frequent, or the value that is most frequent, we refer to that as the mode. But we are not just interested in where the numbers are, but also how they're spread out. And so if we were to take a look at the salaries, as we mentioned in the last video, the salaries of employees at St. Mary's, we want to get a sense of the spread. So the salaries may range from $15,000 to $250,000. That's a sense of variation, how much variation there is in the salaries. But what if the salaries actually just varied between $70,000 and $100,000? That would not be much spread compared to $15,000 to $250,000. So we want measures that would help us to understand just how much spread there is in the data. And so we refer to that body of descriptive statistics as measures of variation or measures of dispersion. And if you think of disperse means to spread out, right? We have a number of measures that we can consider. One is called the range, another is called the variance and its related standard deviation, and the coefficient of variation. So we'll explore these different measures as we go through this short video. So all distributions exhibit what we call variation. And variation in the numbers, because all the numbers are not the same. If all the numbers were exactly the same, then we really don't have a distribution. So just from the term itself, distribute, sort of indicates that the numbers are different, and we want to be able to measure that spread or that variability in the numbers. Okay, so let's get into some of those actual measures. If you look at this diagram right here, you could have two data sets that have the same center value, that is the same median, the same mean, but the numbers are spread out very differently. In this case, in the sort of a narrower distribution, well, the numbers are not quite spread out, but in the shorter distribution, because you could see the numbers are much more spread out. Okay, so the very first and very simple measure that we a lot of us are familiar with is called a range. What is the range of the grades in an exam? Well, the marks range from 25% to 95%. So the range really measures first the extremities, the smallest number to the largest number. And so we could see here the range is the maximum value minus the minimum value. So if the highest mark in the exam was 95 and the lowest mark was 25, then the range is 95 minus 25, which is 70. So a measure of variation that is computed by finding the difference between the maximum and minimum values in the data set, we refer to that as a range. It's a very simple calculation, but it has some issues. One of the key issues with the measure of range, it tells us nothing about what's inside of those two numbers. And so the numbers could be quite the range could sound quite wide when it is possible that the numbers in the center of the distribution could be quite close. So we need to somehow cover for that. But nonetheless, the range gives us a quick and dirty sense as to how much spread there is in the overall data. Now, we talked about quartiles earlier, where quartiles take our data and divide it into 4 equal parts. First quartile meaning the bottom 25%, second quartile will include the bottom 25% and the near middle inner 25%. So in other words, the second quartile, which is the 50th percentile, will have 50% of the data below it and 50% of the data above it. and then the 75th percentile would have 75% below, 25% above. So rather than just focusing on the extreme values that will give us the range, why don't we look on the middle 50%? So what is the range now between the first quartile and the third quartile? So Q3 minus Q1. So that middle 50% will give us what we call the interquartile range. And so it eliminates the outliers, the extreme values, and looks at the center of the distribution and say, what is the range in the center? So that's actually an improvement, but remember it only measures the range in the middle 50% of the data. Okay? If you look at this diagram, you see what I'm talking about. So if we use this diagram, which is typically referred to as a box and whisker plot, you have the minimum value, the maximum value, and then what we then do, this is actually x maximum, not x minimum. This is the first quartile, second quartile, third quartile. So you see the 25, bottom 25, next 25%, and so forth. Well, the interquartile range would be that middle 50%. So Q3 minus Q1. All right? Is how we would do that. There's another very important measure. Now this one is different from the last two because now it requires that we measure how far the numbers in the distribution or in the data set are from the average of the numbers in that data set. So we're not just going to just take the extreme values and look at the distance between them. We're saying take the average and look at all the other values in the distribution. How far are they from that average? And so now we have this sort of very calculated measure of variation or dispersion. So it, by definition, technical definition that is the average of the squared distances of the data values from the mean. So we could see here, if it is a population we're talking about, our sample size is often referred to as capital N. So mu, this Greek symbol, is the average of the population. So if we took each value in the distribution, find its distance from the average, population mean, and then square them. The reason why we're squaring is because we're not interested in whether or not the number was smaller than the mean or larger than the mean. We just simply want to know how far it is from the mean. So we square those numbers, and so we'll get the sum of the squared distances from the mean. And if we average that by dividing by the number of values in the sample, or the population, sorry, then we will get a value that we refer to as the variance. Okay? As the variance. Now we have a shortcut formula, and that formula is actually derived by expanding the numerator here. Trust me, it may look a little simpler, but this formula is a lot easier to work with. Okay? Now there is the standard deviation, which is related to variance. Not so much an issue, but the thing about variance is that the order of the values is of order 2 squared, because we squared all those values to get the variance. So that means the values are the order to order 2. But if we want to bring it back to order 1, we need to take the square root of the variance. And so now we bring it back to level 1 or order 1, if we want to call it that. And we refer to that measure as a standard deviation. So the standard deviation is just the square root of the variance. So if you have the variance, you could find the square root of that. That gives you the standard deviation. If you have the standard deviation, you could square the standard deviation, and then you would get the variance. So the two things are totally related. Okay? So the most commonly used measure is really standard deviation, not the variance itself. Because we would, excuse me, we would like the measures to be of same order of magnitude as the values that we used in calculating it. Hence the reason why we want the square root of the variance. Excuse me. So let's continue. If we wanted to do a calculation involving the sample standard deviation, we would not use this formula, of course. This is the variance, sample variance, and the square root of the variance would be the standard deviation. But rather than using those formulas, we would use a shortcut formula as well. But just before I do that, I just want to show you the difference here. When we're talking about a sample, our sample size is n. But note that instead of taking the sum of the squared distances and dividing by n, we're dividing by n minus 1. And I will explain that a little later. But that helps to provide what we call an unbiased estimate of the population variance. So this sample variance estimates the population variance sigma squared. If we want an unbiased estimate of that, we divide by n minus 1 instead. The statisticians have found that that gives you a better estimate of the population variance. There is a shortcut formula that we could use, and you've already seen the shortcut formula for the population standard deviation, well, population variance. If we just take the square root of that, we'll get the population standard deviation. And here we will look at the sample standard deviation by taking the square root of what's inside of this bracket. Note now that we divide by n minus 1 when it's the sample, but n when it is the population. The steps in computing sample variance or sample standard deviation is fairly simple. Once we have the data set, then we decide which formula we're going to use. If it is variance or if it is standard deviation, we must compute the mean. That's if you're going to use the long formula. If we go back a little bit, if you're going to use the mean in the calculation. But if we're not going to use that and use the shortcut formula, then there's really no need to calculate the sample mean or the population mean. We would simply use the sum of the x's and the sum of the x squared. So the values in the distribution, we would add them up to get the sum of the x, and then we would square the individual values and add that up, and we get the sum of the x squareds. And then all we need to do is to substitute in that formula. So you could see here, this is the sum of the x squareds. So if my distribution had values, let's just take 5 values, say 1, 2, 3, 4, 5. Then the sum of the x squareds, I would have to square 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. And that would be this term right here. However, what's in here would be 1 plus 2 plus 3 plus 4 plus 5, and I would square that value, and that's what would be in this term right here. Okay? It's important to distinguish between the two. There's a very useful measure called a coefficient of variation, and it's quite useful when we want to compare the variability in different distributions, particularly distributions that have numbers that are of different orders of magnitude. So if we wanted to compare, say, the variability in the price of cars to the variability in the price of a pound of fish, well, the pound of fish is of the order of magnitude, what, $5, $10, $15 for a pound, but a car is in thousands of dollars. So if we just compared the standard deviations or the variances of those two distributions, the variation or standard deviation of the price of a car is in thousands, and the variation or standard deviation of the price of a pound of fish is in a few dollars, right? So you couldn't compare those two, because obviously you'd say, well, since the variability of cars is in the thousands of dollars, then it has higher variability. But that is not true. We need to compare those two things using an appropriate measure. We call that measure the coefficient of variation, which really what it is a relative variation, a measure of relative variation. And it is the ratio of the standard deviation of that distribution to the average of that distribution. So it's a ratio of the standard deviation to the average of the distribution. All right? And it's usually expressed as a percentage. So it is really the variation relative to the mean. So if we're dealing with the population, the coefficient of variation would be the population standard deviation divided by the population mean. If we're talking about a sample, it is the sample standard deviation S divided by the mean X bar. All right? So those two measures, one for population, one for sample, measures for relative variation. Now let me just give you another example or an analogy that may make a lot more sense to you. If I wanted to compare the effectiveness of investments, so let's say I invested in real estate. So real estate is thousands of dollars, and if I invested $100,000, bought a property and then sold it for $110,000, then I made $10,000 profit. Well, what if I bought, say, a piece of furniture for $100 and then I sold it for $110? I would have made $10 profit. So which investment is better? You might say, well, you made $10,000 in the case of the home that you sold. So that's a better investment. But that is when you compare that $10,000 to the $10. But why don't we express it as a percentage or as a yield? So the $10,000 over the $100,000 is a 10% return on my investment. The $10 for the furniture over the $100 that I invested is a 10% yield on my investment. So the two things are comparable. The question is, do you have $100,000 to invest, or do you have $100 to invest? So it's much the same thing. So now we could compare those two investments because we are looking at the yield or the return on investment. Same way here, we could compare two distributions when we compare their coefficients of variation, not their actual standard deviations or variances themselves. Okay, so here's an example with a stock price of $50, standard deviation 5. So we simply take the standard deviation divided by the average, 5 over 50, 10%. Now if you look at the average price was $100, the standard deviation 5, then 5 over 100, the variability is only, the relative variation is 5%. So clearly the second stock, stock B, has less variability compared to stock A, even though the standard deviations are the same. All right? We want to examine a concept called the empirical rule. Now the empirical rule helps us to draw a quick conclusion about the data set that we're looking at. In a couple of lectures from now, in future lectures, we'll be exploring what we call the normal distribution or the bell-shaped curve. And the reason why we'll spend some time with that distribution is because it's a very popular distribution. So the bell-shaped curve is a symmetrical distribution. And one of the things that we know about the bell-shaped curve is that if you were to take the mean, the average of that distribution, and you added and subtracted one standard deviation from the mean, so you add one standard deviation to the mean and subtract one standard deviation, the values in that range, you'd have approximately 60% of all of the values in that distribution in that range. If we now calculated two standard deviations, that means two standard deviations plus the mean, two standard deviations minus the mean, then the percentage of the distribution in that range would be 95%. And then finally, if we were to add 3 standard deviations and subtract 3 standard deviations, then virtually all of the values will be in that range. So we call that the empirical rule. Now what's the value of that to us? Because samples are supposed to reflect their populations, this empirical rule that we just mentioned here happens to do with the population. Notice I'm using population values mu and sigma in calculating the ranges. So what if now I have a sample and I wanted to ask myself, did that sample come from a bell-shaped curve? How would I do that? Well, I would basically employ the empirical rule, because all I would have to do is to replace the population parameters by their statistical equivalents. So the statistics that I would use would be x bar and s, where x bar represents the sample mean and s represents the sample standard deviation. So I would use, instead of mu, x bar; instead of sigma, I would use s. And that would allow me to compute ranges for the sample. Now, if the percentage of values that fell in those ranges are similar to these values right here, 68%, 95%, and almost all, then I could argue that the sample came from a bell-shaped curve. Right? Because remember, if the sample is displaying a similar characteristic to the population, when the population is a bell-shaped curve, then that sample could have come from a bell-shaped curve. All right? So this is the diagram that sort of illustrates for us what we're talking about. Here's the mean. This is a symmetrical distribution. So if we add and subtract one standard deviation, we have 68%. Two standard deviations, 95%. And then three standard deviations, almost everything. Okay? Now, what if we're not sure if the population is a bell-shaped curve? Well, there's Chevys theorem, which basically says, regardless of how the data is distributed, at least 1 minus 1 over k squared of all of the values will fall within k standard deviations of the mean. So what is k? K represents the number of standard deviations that we will add and subtract to the mean. So if we use one standard deviation, right, then it says here, for one standard deviation, then at least 0%, well, that makes sense, would fall in that range. So you can see this is highly conservative, of course, right? If we look at two standard deviations, then at least 75% of the values will fall in that range. All you do is you substitute k is equal to 2 and compute this value. And then if we look at three standard deviations, at least 89% of the values would fall in that distribution. So we could actually sort of try to empirically test this theorem by taking a data set and then computing these ranges and then testing to see whether or not the percentages here are adhered to. Okay. The last thing I want to expose you to is a value called a standardized value. So standardized data value, and then let's pay attention to the term standardized. So what happens now is that if we are looking at, say, values in a distribution, and we have the average of the values and we have the standard deviation of the values. Well, remember to calculate the standard deviation, we had to look at how far all of the values in the data set are from the average. Now, if we were comparing different distributions, remember we said that the values in the distribution can be of different orders of magnitude if we're comparing different distributions. They can be of different orders of magnitude, so it does not make comparison of multiple distributions easy unless the numbers are of the same magnitude. So that's why we use the coefficient of variation. One of the things that we would like to be able to do is to measure the distance between the mean and any value in the distribution. But we want to measure it in such a way that we have what we call a standardized measure. One of the ways to do that is to take the distance and divide it by the standard deviation, and we will refer to that as a standardized value. So if you look here, in this case, for a population, here's the population average. If I take any value in that population and I subtracted it from the mean from it, that distance, if I divided it by the standard deviation, I will call this a standardized value. So let's just take an example. If the standard deviation was, say, 5, the mean of the population was 20, and I'm looking at a value of 40. So 40 is 20 units different. There's a difference of 20 units between that 20 and 40. But if I divide it by 5, that 20 divided by 5 gives me 4. So what I'll be saying essentially is that 40 is 4 standard deviations away from the mean. 4 standard deviations. So that's the way in which we would speak it. We would say that Z represents the number of standard deviations that a value is away from the mean. And that has great significance later on, as we will discover as we move to the other chapters, chapter 6 in particular. All right? So Z scores, another way to think about a Z score, think of it as if I'm standing, say, at one given point, and I threw a rock. If that rock, say, I threw it 200 inches away, then let's say if I wanted to use a standardized value of feet, I want to express that distance in feet, I would divide by 12 inches. So I would divide that 200, or however many inches that I said I threw that rock, by 12. That would allow me to express all the values in feet. So maybe I'm using a foot as my, as my unit that I'm interested in. So that's how I would standardize all the distances. Well, here we want to standardize the distances in standard deviations, hence the term standardize. So Z would allow us to take all those distances and express them in standard deviations. And so remember that whenever you see Z in this case, in this context, it means the number of standard deviations. So if Z is 2, the distance that we've just measured is 2 standard deviations. If Z is 5, the distance we measured is 5 standard deviations. Okay? And that's a very important value that we want to be able to use. So here's an example where we're looking at IQ scores. The mean is 100, standard deviation is 15. We find an observation of 121, then express that as a standardized score. We would subtract 121 minus 100 divided by 15, 1.4, which basically says that the IQ, so the person's IQ, is 1.4 standard deviations above the mean. And at this point you're asking, well, yeah, that's great, but what's the value of that? It will come in a bit later, because the further, the higher the standardized value, the more extreme the value. That makes sense. I mean, if I had an IQ score of 200, then that would certainly be a much bigger Z value. So the Z value kind of gives us a sense. The bigger they are, the further the numbers are away from the mean, and that has significance in probability when we come to that point later on. So we hope you appreciate this segment, which actually looked at the measures of dispersion, or the measures of variation. And we had several measures. We talked about the mean, not the mean, sorry, the range, the interquartile range, the standard deviation, the variance, and the coefficient of variation.